In this lecture, we're going to look at two more integrals that we can evaluate using our new integration by parts technique that in different ways are kind of interesting. So take a look at this one first. We've covered, either in this class or the previous one, integrals of pretty much every elementary function, right? We've done polynomials, all the trig functions, hyperbolic functions, exponential functions, but not the logarithm. Right? We haven't talked about how to integrate this thing. And the reason is we need this integration by parts method to do it. Now, it may look kind of odd at first because there's not the usual two things being multiplied that we've seen in every other integration by parts example. But here's what I'm going to do. I'm going to let u equal the log of x. Remember that's the part that I maybe can't integrate, but I can definitely differentiate. And then over here, I'm just going to let dv equal dx. Okay, well, so now differentiate the left side. Du equals 1 over x dx. And if we integrate over here on the right side, v is equal to x. Okay, let's put this into our formula. The integral of the log of x dx is equal to, and we do u times v first, that's x times the log of x, minus the integral of v du. Well, that's x times 1 over x dx, and that's going to be nice, right? The x's cancel. This is x log of x minus the integral of dx, and that's just x, right? So the whole thing is x log of x minus x plus constant, right? There you go. Right, there's my answer. That's the family of antiderivatives for this function, for this integral. All right, so what we did here, right, we've kind of done something similar. We've let u equal x. Well, this is kind of the equivalent, right? Letting dv equal dx, and then, that's fine because we can integrate that. All right, so how about this thing, right? How am I going to integrate this? Well, here's what I'm going to do. I'm going to let u equal x squared because I can differentiate that. And I'm going to let dv equal e to the x dx because I can integrate that. Okay, so this means that du is equal to 2x and v is equal to e to the x. So if we do what we've been doing, right? The integral x squared e to the x dx is uv. That's x squared e to the x minus the integral of 2x e to the x dx. Excuse me, I left the dx out of there. That's 2x dx. Okay, well that's interesting. So let's pull that 2 out just because we can. This is x squared e to the x minus 2 integral of x e to the x, which I also don't excuse me, don't know the antiderivative of and antiderivative of it. We did do this one in the previous lecture, so it would be for me a fair ball if you went back and just pulled the answer from there. But at this point, if you don't know that integral off the top of your head, your next step would be to do integration by parts again, right? To do it a second time. So this time I'll let u equal x and dv equal e to the x dx again. So du equals dx, and that I'm feeling good about. That's going to go away in the integral part. And v equals e to the x. All right, so let's do it again. This is x squared e to the x minus uv, which is now x e to the x, minus the integral of v du. So that's e to the x dx. And that one I can do. So this is x squared e to the x minus x e to the x plus, I'm distributing that minus sign in here, right? Plus e to the x plus a constant. There you go, right? There's my answer. There's my integral. So the takeaway from this one is sometimes you have to do this more than once, right? I was kind of using this process of letting u be the polynomial parts, letting u be x squared, and then when I differentiated, that went from a squared down to a first degree term, and then I did it again, right? And I was kind of using the differentiation here to sort of whittle away at that variable, right? Until eventually that term became just a constant. And when the variable went away from the integral, okay, I was able to do it in a very straightforward way. Okay, so now you've seen several examples, some of them basic, some of them maybe not so basic, of ways that we can use integration by parts to evaluate specific integrals. There's one more lecture to go in this integration by parts series. In the next and final one, we're going to take a look at some examples of how we can do definite integrals using this integration by parts technique.